So my name is Jack Vargas. I'll be your humble host for today. I am an engineer on TV, so I'm part of the evil marketing organization, I guess Death Star Incorporated, I think is what we got branded today. They're going to launch a planet, blow a planet up. Sounds good. All right, so first off, I want to thank our wonderful panelists for taking time out of your busy day to be here. So I'm going to lay down the framework, then I'll do a quick introduction for our guest here. So I'll kick off the panel by asking a question, surprise there. After that, I'll open up to the audience for questions. Our wonderful Marty will be running around with the mic as well. You can tweet me at Jack_Vargas. I'll have Hootsuite running up here. For those who tweet me, you get a chance to win an Apache Pass DIM. And by Apache Pass DIM, I mean a picture of an Apache Pass DIM. Marketing. All right, so let's get into introductions. From GridGain Systems, we have Nikita, who's founder and CTO of GridGain Systems, founded in 2007. He has led the development of advanced distributed in-memory data processing technology. He has over 20 years of experience in software application development and is a pioneer in using Java for server-side middleware development. He's an active member of the Java middleware community and contributor to the Java specification. Welcome, Nikita. Thank you. Brian. Brian is founder of Aerospike and currently CTO and product, and a wizard of networking, which I think meant of people networking and networking.
No. Packets, packets.
Packets. Wizard of packets. Brian has a deep technical background from being lead engineer at Novell, chief architect of cable solutions at Liberté, and director of performance at Aggregate Knowledge. That's just his day job. Brian also plays the cello, as well as writes about cuisine in the San Jose Metro. So if you need questions, there's an idea. What's for dinner? Thank you, Brian. Scott. Scott is a technology fellow at DreamWorks Animation. He currently guides the technical direction of the studio's infrastructure technology, which means he is responsible for the computational visualization infrastructure required for creating these amazing 3D animated films. Scott has many years in the entertainment industry with credits on over 30 productions, including The Boss Baby, which I think starred the best Baldwin.
And got nominated for an Academy Award.
And nominated for Academy Award. Prior to DreamWorks Animation, Scott worked for Walt Disney Feature Animation, as well as the aerospace industry. Quick sidebar, I think Andy and Jenny know, but usually when I dress up, I wear fun socks. I have R2-D2 socks and Steven's Star Wars theme you had for today. Anyways, if you could hook me up with some, How to Train Your Dragon socks, I would appreciate it.
I'll get you a picture of one.
Ouch. All right. And last but not least, Kodi. Kodi is a vice president at Oracle Corporation. He joined Oracle in 1997 and has over 20 years of technology leadership. His main responsibilities are development of Exadata, and has previously developed clustering solutions at Oracle. Welcome. Thank you. All right, thank you, panelists. So first off, I'd like to start by giving the panel an opportunity to explain where they are with their journey with persistent memory. So please keep around 5 minutes, and we'll start it off with Scott.
I win. All right. Is this thing on? So persistent memory is an interesting topic for us. Sitting here today talking to everybody, listening to all the pitches, everything's very data center centric and large compute centric and databases and file systems and stuff. We're trying to move persistent memory closer to the end user. I want it to make humans more efficient, not storage systems. So it's a different perspective on what persistent memory does for the users. Everything from application startup time to being a file system cache. And the case I think is most interesting is we're trying to use persistent memory in end-user workstations as a data structure shared thing. I don't know exactly how it's going to work, but if you're not familiar with, so feature animation is the official term, but I get to make cartoons. And cartoons are creative, and creativity is iterative. So our artists spend an awful lot of time coming into work, reading notes, booting their workstation, loading an application, lather, rinse, repeat on their data set, and saving out some deltas. I want my artists to make art, not wait for files to load and data structures to serialize and memory to get populated. So our first first crack at persistent memory was as application redo data set logs such that the application would start faster, right? It's been sort of a solid state thing that Windows and other operating systems have done for a while is the stuff you use, keep it close. The next step that we want to try to accomplish is sort of like a fabric, but I want to do a shared global namespace to find existing data structures somewhere in persistent memory, as opposed to reading a file, making my version of it, putting it in persistent memory. The real problem I have with persistent memory is the pictures of the Apache pastims are really expensive. And I don't want to strand them inside everybody's workstation. I want to federate them across the entire enterprise. So it's sort of a fabric vision, but it's with end-user workstations, not with data center gear. So, and where we are today, we're testing with PCI devices, MEMMAP on top of them for the programming model experience, and thinking about how we restructure applications to take advantage of persistence, both for application start time, for data set sharing time, and then there's a third wrinkle. We use a lot of third-party software that's never heard of persistent memory, and we have to figure out how to integrate that as well into the same namespace. So a POSIX API to the same shared data space becomes necessary, as ugly as POSIX is.
Thank you. Kodi, where's Oracle and yourself in this persistent memory journey?
Hey, let's just, okay, great. So where we're at is, it's actually kind of interesting. Many people know the Oracle database. I run the development of a product called Exadata. Just at a high level, it's scale-out storage with scale-out compute. The compute is where you run your database and you scale out your storage. So you can sort of elastically open anything that you want, expand your capacity, expand your compute needs. And what we saw was really a way by which we wanted to make sure that you can use this everywhere. By the way, Exadata is used everywhere, okay? Every time I do shopping on my weekend, it's used all over the place. Every time you guys flew in, all you guys were checked against an Exadata, okay? So it's very, very cool, and it's very satisfying. And so we wanted to make sure that all those use cases benefited. So a storage use case, we want to benefit that. A columnar database use case, we want to make sure that you have a benefit for that. So we have use cases by which you can have the persistent memory show up on a database server, show up on a storage server, and sort of show benefits for everything. And the way we do that is, think of it as, hey, you have persistent memory, and we know that it's larger, it's a little bit slower, and so you can say, all right, it's a tier of memory. Once you're done using your hot index root block or something stays in your regular memory, sort of the colder data, drop it down into this persistent memory that's out there, compress that a lot better, so you can store a lot more columnar data for the database inside this persistent memory. And when you look at storage, we're scaled out, okay? So it's very cool for us because you can add a tier of persistent memory. We have flash tiering on top of regular hard disk. You can add a persistent memory storage tier. And what was very cool for us is that we had RDMA working already for us. And so we had to essentially complete that loop with persistent memory and make sure that you can RDMA from storage and have very, very low latency for storage. So think of it as all your database IOs running in like single-digit microseconds. That was the goal. And as of last Oracle Open World in October of last year, we showed a demonstration. It was very cool and personally very satisfying because we showed, we had like over 1 million IOs running, 0 CPU utilization on the storage server. Just fantastic. Everything just running through RDMA. We were actually soaking up an entire 100 gig link, and the CPU just didn't even move. And that was fantastic for us. We could store a ton load more data on the compute. And so when you take benchmarks like industry standard benchmarks, I can't name them, but industry standard benchmarks, they showed like enormously powerful performance. And so what really excites me is that we are now expanding the use cases. It's not just the storage is faster, your in-memory compute performance is faster, but it's really expanding the use case of what you used to do. If you were doing inventory management over a year, you can do inventory management across several years. If you're trying to do network intrusion detection, you can do that a lot faster now. So you don't just have to go through sampling, you can go across the entire data set. And those are the things that we're really excited about. And just where we are now is it's really kind of fun. I have these toys. You know, the pictures, I have real toys of those that we're kind of playing around with. And, you know, we work with all these guys, okay? So like Jack asked me, hey, what are the resources that you have? You know, pmem.io is a great resource. Having Andy's email and phone number is a even better resource. And, you know, Dan, you know, we started working with Dan, you know, like I don't want to talk on this panel like last year. This year, we're just so excited. Dan's work in device stacks is just fantastic, okay? All the huge paid support just really, really works. And so at this point, we're like, hey, this thing is stable. It's actually working. It's just like run to product at this point. So all the code is kind of working. It's just like, hey, let's just productize and get it out of the door. So it's absolutely fantastic, and that's where we are.
Great, thank you. Noted. All right, Brian.
Hi. So how many of you have heard of Aerospike? Oh, great. So where Aerospike is I think you have a really nice panel here, by the way, because there's 3 different kinds of database folks here. So what you just, and a user of all of them. So you got a really nice spread here. So if I was just going to compare and contrast what you just heard about Exadata, right, which is really big query support, being able to push queries into your data set, then GridGain is really great at moving compute to data and that whole set of optimizations. Where Aerospike fits is we're really a row database. So we focus on making individual row access order 1 fast across big data sets, petabyte scale data sets. So in 2013, I had a serious problem, which is I built a database that is really predicated on Flash. All of our our data structures, I just said, look, we're not supporting rotational disk. This whole thing about B+ trees and all that stuff, you know, forget it. We're going to build an entirely new data structure. And that's one of the reasons Aerospike's been successful. But that data structure is predicated on putting your indexes in RAM and thus driving the parallelism that you need out of NV RAM. So, and DIMMs. So in order to do that, we usually need about 2 to 3 to 6% DRAM to flash ratios, which seemed okay back when we were dealing with 400 gig drives and maybe 16 of them per server. But as we started rolling up to 10 tera and 50 per machine, you do the math and you're back into needing 6 tera to 10 tera of RAM just in order to provide the indexes. So I was getting a little worried about our architectural approach. In order to support these kind of high density devices, luckily, along came the persistent memory technology, and the fact that we already had an internal software architecture that allowed us to separate out index-oriented work from pure storage block reads meant that we had a great technical path to be able to actually start working with interfaces like PMEM and the kind of devices that we've had to gotten from Intel. So where we are in our journey is, I'm going to echo exactly your thoughts, which is, this shit works for us. And I now have, it works, it's great, it really does. The performance numbers we have, one I can't talk about, but what I've been told I'm allowed to say is the performance is on par, right? So the idea that I can now have 2 to 4 tera of RAM-like substance and put all my indexes in it and get my nice access to my rows, which are all in Flash. Those are still taking, say, 70 mics to go and do my individual reads, but my index traversals, which are going to be multi-step, I don't really see a difference in performance. And restart times, of course, are negligible, right? It's down from 10 minutes down to, 6 seconds or something like that. So, so far experiments are good. Our code is pretty much complete. We're waiting on these DIMMs, and I got a stack of customers who want it.
Thank you. Nikita.
Yeah, so I'll try to be pretty short because I think I can probably echo everything this guy said. We're a little bit of an odd duck here. We're Java-based software. So we're, you guys think about in the OS level, driver level, we don't really care about OS level behind us, really. So we're on the Java level. So for us, we looked at the whole non-volatile memory probably about 5 or 6 years ago, really the very beginning. Talked to pretty much every goddamn vendor in the valley about it. you know, we have a little bit perspective here, a little bit different. So we don't really care about block level device. So block level thing for us is a non-issue. You know, it's for us it's just extra faster drive. That's all there is to it to us on a Java level. And we've been struggling to find for the last 3 or 4 years to kind of find any workable anything that is byte addressable. And you guys probably know that's been coming slow and still not there yet. So for us, the byte addressability, for us, I mean the folks that actually operate on the Java ecosystem and up, any kind of virtualization of a language, runtime. For us, the byte addressability that's baked in an operating system, baked in the OS APIs, is absolutely necessary to gain the interaction. Think about this. It may be a little bit foreign to you guys, but for us, for example, to support some C-level libraries like in MM and whatnot, would literally require to bake away from a kind of Java advantage of running everywhere and start supporting every goddamn version of Linux and kernel and whatnot, which is a huge problem for a smaller company. So for us, and that's, has kind of double effect that, most of our customers, they run us for pretty much, mission critical applications and financials and whatnot. And they also look at us to adopt this technology. So there's a bit of a chicken and egg problem. We're waiting for vendors and operating system guys to really get the byte addressability into the OS, stable, API'd, baked into Java. So then we can go back to our customers and say, look, there's a wonderful thing there. And they basically say, well, whenever you guys have it, talk to us back. So we kind of caught a little bit on this kind of chicken and egg problem. We've been proponents of this for literally, I'm telling you, 5 years, if not more. And we obviously have some use cases, not some, but dozens of use cases where people use us for block level, not us, but using the NVMs and the NVMe specifically for as a basically faster drives everywhere. Again, from a Java perspective, we don't care. For us, it's just a normal block level device, just like anything else, just a little bit faster. But the byte addressability is absolutely key for us. That will open floodgates. Believe me, there is there's a one Exadata, there is just one thing, there's thousands of open source projects that will benefit from that. An ecosystem of those projects is 1,000 times more than one particular vendor. So we all, we run the top project in Apache Software Foundation with Hadoop and Spark together. So we're all waiting for this byte addressability that is becoming a standard within JVM. The minute we have it, you wouldn't believe what changes will happen pretty quickly.
All right, thank you. Want to check, are there any burning questions out there in the audience? Raise your hands if seeing out there, Mr. Pappas.
I have a question for Nikita. Are you involved at all with the open source persistent memory JVM project?
I'm aware of it. No, we're not. Okay. No, we're not. Again, for us, it's I don't want to come away as a complaining guy here, bitching about something, but it is open source companies or just open source project or just the companies around them, they're fairly small companies. It's very hard. Ask anybody. Ask Databricks, DataStax, and Cassandra. Ask a bunch of Hadoop vendors. They tell you the same story. It's very hard to support something that's just specific to a specific Linux kernel or specific version of library. We're not there yet because go to every customer in the world, they will have something different. So we need to have that baked into the, for example, JVM for us in Java world. So back to the Oracle folks now. The minute they have it in the JVM level, that will basically be explosive growth. Because right now, look, whenever I'm asking, like I'm going to a major bank in Wall Street, I'm asking about NVM, one guy out of 100 we know what the hell it is, right? Because it's a pretty tough stuff. The minute we have it in JVM, every developer on the application side will know what it is. And it will be automatically explosive growth.
All right, thank you. I think we have a question up here in front. Tom?
This one's for Scott in particular. Scott.
Thanks, Tom.
Yeah, good to see you. How do you think that persistent memory is going to be changing movie workflows?
The holy grail for us is something that so a little movie 101. So 90-minute movies chopped up into 50 sequences, chopped up into 1,500 shots, and each shot's a frame. Right now we have enough memory in a given machine to maybe work on a shot 80 frames or so, 5 seconds worth of animation. The goal is we want to do something called sequence-based or whole film-based development. Oh, and within that shot, we use a decimated version of the models, a decimated version of the environment because it won't all fit in memory. But if I can get 200 or 300 or 500 terabytes of federated persistent memory to hold all my assets and all my derived work, then I can work on the whole movie at the same time. I can't do that today. I can work on the movie. It's painstaking. Our animation team, for example, if they do 8 seconds of animation a week, it's a good week. So the reason it takes 5 years to make these movies is some poor schmo is moving characters around on screen for 8 seconds a week. And part of that is that he can't see what's before him, he can't see what's after them, he can't see the other characters in memory because these things are memory huge and core huge. So the big goal, to answer Tom's question, is I can do more collaborative parallel work than I could ever imagine doing. It's a little bit like the Aerospike challenge. I can have a bigger database.
Great. I think up front first, then we'll go to Death Star guy, anti-Death Star guy.
If we look back as little as 10 years ago, we had a three-tier hierarchy: RAM, disk, network. What we've been presenting to you guys today, you put that together and you have literally dozens of tiers of performance in this hierarchy. You put them together in combinatorials and you could have some really significant challenges in terms of load balancing. How big a challenge is that to you guys, and what can we do for you to make your job easier in using a heterogeneous memory subsystem?
I can take that one. As a real live end user, the biggest deal is everybody has to play with the same standards. If I have to figure out that that port will talk that protocol to that thing, but that one won't, it limits my choice and forces me down bad paths. So stick to the standards, don't try to invent your own, or invent your own but share them with everybody.
And to add to that, I really like the tiering that we have today, because what it really allows us to do is take the cost of, let's say, like a hard disk and give you sort of a performance of flash moving on to like persistent memory that you can use as a cache in front. And so as a customer, you're able to get, hey, the lowest cost for a large amount of my storage, but sort of very high performance for the working set that I really needed. So I think it's very, very helpful to have these tiers. And it's just a matter of sort of figuring out where these tiers actually fit in and where the more useful ones are. That's very helpful for us to do. But I think just in terms of gluing all these tiers, I wouldn't go by doing that because I think it's going to be on a per application basis where the actual tiers make sense. But having these tiers helps a lot because it reduces the cost for the customer but gives them the performance when they actually want to do that work on the active working set.
Can I ask the panelists, so it's Persistent Memory Summit?
Can I answer that real quick?
Oh, sorry, yeah, go ahead.
I have an answer. First of all, I'm going to argue against tiers, but that's kind of a dumb statement. They're not really tiers because each thing is different in slightly different ways. But the right answer is we need better orchestration mechanisms, right? So, which I think is what you're asking for also, which is, VMware, that sounded all well and good, but I've worked with, we currently have too many orchestration mechanisms. I'm liking Kubernetes right now and what they're doing, but when you look at how they think about remote storage and the lack of complexity within storage virtualization, you don't know how fast things are, you don't know how far away they are really, you've got these devices, you can't get access to it's terrible. So that's what I need, is I need better orchestration mechanisms.
All right, Stephen, go ahead.
I guess one of the things I'm interested in understanding is it as much about the availability of more and cheaper and lower power memory, or is there something in the persistence for you guys that really makes this more than just being able to get more data into a memory-centric footprint? What is it about the persistence that you guys really like?
Do you want me to take that first? So I'll tell you, the one thing that I really like is sort of melding of two technologies together. One is the persistent memory. The other is the ability to do RDMAs. And sort of today, just take any server, right? If you want to have like a single storage with some local storage or something like that, for like a mission critical database, it's kind of not interesting. Just because, hey, that server fails, some DIM fails, some component fails, you can't keep up. So scale out is really helpful for us, and making sure that there's a copy of data on this server, a copy of data on that server is very important for us. And when you have persistent memory, the nice thing about it is that we're able to do RDMAs, which means that I can do everything one-sided. So the compute server is doing reads and writes in a one-sided fashion without waiting for a context switch, wake up, perform localize, all the kind of nonsense goes away. And so you can, today, for example, with the Optane SSD, for example, it's got like fantastic low latency. But still, you got to go through the wire, get a context switch, wake somebody up on the other side, have them do the I/O. It's all complete garbage. When you have this persistent memory, you can just one-sided start doing reads and writes, and that's really where the difference lies. So it's not just like cheaper, larger memory. The persistence plus RDMA opens up a huge amount of storage characteristics that's completely different from what is available in traditional storage. That's really what is attractive for us.
So I'll answer slightly differently, because as part of the newer database community, NoSQL and beyond, we think kind of in a complex way about cap theorem, right? And so once you start thinking about AP databases, persistence, people get a little less, I must have my persistence, every byte must be committed. So I see probably the benefits of this much more being closer to fast RAM than being persistence. And what we also know is the people who really care about CP databases tend to have small data sets. Now, I'm hoping that changes in the next 5 to 10 years, and I can go sell them a shit ton of databases. That you really do need strong consistency petabyte data stores. But that day isn't here yet. So Aerospike is introducing strong consistency. We're crossing the AP barrier, and I do think that these levels of persistence are absolutely necessary for us and pretty interesting. So I love it all. I get cake, I get to eat it. It's awesome.
Can I take one whack at that before we go? Being big is important. Being fast is important. Being persistent lets me simplify things. Right now, I have a very clear mindset of what's storage and what's memory. When my memory remembers forever, then I don't need storage anymore. So we're planning to collapse the hierarchy between working set, memory, storage, tier 2 storage, offline storage, backup storage, and it's just stuff, right? It introduces some, it's just the software stupid type issues around how do you do durability, how do you do availability persistence, how do I get business continuance, how do I get data protection, all that crap. But those are all data problems. They're not really storage problems. We make them storage problems, but I just got to figure out how to put my data someplace. I only want one place, and it's in the address space.
It might be in your database.
And you could be the database. I don't want a database. I just want data. You want a database? That's fun. That's fun to do. We all agree. That's fundamentally the problem.
Sell your database.
This byte goes in the database. This one goes in Aerospike. This one goes in Teradata. This one can go in Cassandra. I just want data. I don't have to think about it.
But I want to point out one other thing, okay? We went down this path earlier where we thought, hey, we can just extend everything that we have in memory straight into storage. But I think when you start getting into, hey, I have like a cloud user base that I need to support. There are tons of users, and you can't really extend that seamlessly because that customer wants to encrypt their data with their own key, and you really got to make sure that that data is visible only to them. And that's really where it sort of starts breaking down. It's like, well, when I want it in memory, I want it to be able to be it in clear text and do work with it. Whereas when it goes into any sort of persistent medium, it's got to be encrypted such that nobody can steal it. And so the real extension of memory down into like persistent storage starts breaking down a little bit with encryption. That's what we see.
Well,
Yes.
there's actually a technique you can process on encrypted data too, but that's future.
Yeah.
Sorry, just one check. Nikita, it looked like you were. I just wanted to double check.
I don't want to too much echo, but if you would talk to the kind of my friend's ecosystem with all this, the Hadoop and Sparks and Ignites and whatnot, for us when we talk about it and the non-volatile storage, we don't even consider a block level devices. For us, that's just not even part of that. For us, non-volatile storage is byte addressable storage. Everything else doesn't even exist for us. We don't care. Think about it. Why do we care about faster disk? It's fast, okay, so what? So we care about something that is the RAM that doesn't go anywhere when you unplug the power. That's a big deal for us. right? We can now think about something else. Faster disk, we don't give a crap about. There's plenty of faster disks.
Thank you. Go ahead.
Yeah, this question is directed to Scott Miller, but it's derivative to the entire group. It has to do with rendering engines.
Sure.
And I've done a lot of rendering, and let me tell you, it has not been pleasant.
The results are nice, though.
Sometimes. That's when it gets worse, when they're not that good. And you know you're going to have to do a lot of work, but you also realize that the amount of time it's going to take is you're not going to meet your deadline, in other words. So that's when you look around and you start cheating like crazy. You do anything to get around it. The product suffers because of that. Specifically, what I'm talking about here is Disney put out a paper on deep scattering on the cloud. You know, Allie Ray Smith years ago said, clouds are hard, we're going to have to cheat. And everybody's been cheating, but nobody makes good cloud because it's a physical monster. And this stuff works. Those clouds that they showed in their paper works. And it takes a 36-hour render down to 9 minutes. And this uses neural networks or neural network technology. They don't mention how much memory it takes, but I subsume that it's rather major.
Yeah, if it works the way I think it does, it's volumetric. So
It's definitely volumetric.
And volumetric, you can make them sparse. Clouds are actually pretty sparse, but it's an awful lot of memory. And I think the Disney renderer does a lot of out-of-core type stuff because they can't get enough memory in the address space. So they spend an awful lot of time paging out, essentially. But it still made it go faster because essentially they're simulating clouds and procedurally generating them instead of physically figuring out what they look like with light. Our renderer does some of the same thing, but clouds in particular, humans are really good at drawing clouds. And as much as we like to claim this is a computer-generated movie, we have map painters still, people whose job it is to paint clouds and will composite it into the back of the. I'm not making that up.
Yeah, it's fun to watch them too.
Yeah, right. I mean, render what you can and draw the rest. It's not cheating. It's art, right?
No.
And
Yeah.
and
this is
something
an art.
about
Remember
art's never complete, only abandoned.
Well, the point
Da Vinci
going
said that.
The point going forward is this is going to have to get real time in virtual reality eventually.
It is at some point, but we're lucky we don't make physical reality. We get to make cartoon reality. So as long as it's believable, it doesn't have to look like real life. So it doesn't have to be virtual reality. Most people's interactions are either games where they don't have to look real or real, and it's friggin' hard to do. So we made a conscious choice. We don't do live action visual effects. We do animated movies. We can take you places you can only imagine, but you have to imagine that they're reasonable, right? So the big switch for us. So we have a new renderer coming out in the next film, How to Train Your Dragon, March. Mark in your calendar. It's a path tracer. So it's a physically based ray tracing, just multi-machine distributed. Can spin all the cores, use all the AVX lanes, can use all the network bandwidth I can get between boxes, and it scales pretty linearly because I can subdivide the geometry pretty well. It does a great job on clouds too, but clouds, hair, fur, anything that's sparse, really hard to compute because light interacts funky with clouds.
Well, sparse is the first word in sparse. What's the next word? Distributed representations. Guess what that is?
Yeah.
Yeah. Okay, thank you.
So.
Thank you. I think we have a question in the far, at the exit door.
Oh.
Mr. Yaya. I'll check Twitter, see if anyone's taken me up on my dim pictures. Nope. Yeah. No tweets from Donald yet. Sorry.
So this one kind of goes back to, I guess, we'll start with Scott, but I think it's kind of pertinent to all you guys. There was one statement, somebody said that there's 3 database developers and 1 user, which is interestingly, because like when we were talking about clouds, like if you remember Puss in Boots and the twisting tornado you guys did, right? The technology used on that was OpenVDB. It's not exactly a database per se, but it's kind of sort of along the lines. The thing about it is that if you look at a lot of both the database internals and you look at file formats in general, like VDB or EXR, all the ones that are used in the film industry, they were designed in a different time frame, right? there, you know, with VDB itself, it's a 4-level data structure. You know, it's very scalable, incredibly well built, well engineered. But does something like that, which the whole industry pretty much uses across the board, right? OpenVDB is kind of pretty much the de facto standard for volumetric simulation data, right? So going forward, how do you evolve that? Because it wasn't really designed for striping or distribution per se, right? Yeah. It was designed for a workstation and interoperating across tools. Now we're in a world where we're having, you know, many SSDs, NVDIMMs, the capacity is getting bigger and bigger, and we're going to a much more distributed world. So all of these existing file formats, do they even make sense anymore? And then are we back to another database?
Yeah, no, they don't make sense. And so OpenVDB and EXR and these other formats, they're on-disk interchange formats.
Exactly.
They're intended for me to write something out and give it to you to work on.
Mm-hmm.
I don't think they make sense at all until the movie's done. So I want to spend 5 years with my data in data structures in the address space and then write out OpenVDB files at the end. I don't want to necessarily carry those around. They're a great way to get an immutable version of some geometry, and they're a good way to hand something to an outsourced vendor, but they're a terrible format to work on. And we spend an awful lot of time reading in EXR files and doing transforms on them and laying them out in memory, and then they're a data structure. And I want to leave them as data structures in persistent memory and work on it for a couple years.
So what you're asking for, to a certain extent, is kind of like Smalltalk from the 1970s, where they bypassed you know, everything. They actually had, you know, loading byte, you know, tiny little objects and big objects and whatnot, right? You want a runtime system that's persistently aware. That's what it sounds like.
But I also want to try to avoid transforming the objects. I want to leave them in their working state for the most part, so I don't spend time serializing, writing down, deserializing, and reading in. I just spend time doing the work. So one of the first things we have to do is design APIs around in-memory data structures instead of around file systems.
Mm-hmm.
We're going to try to spend some time around a namespace. It's got to have a hierarchy, and it's got to have versioning, and it's got to have multiple dimensions. Probably have a key value store or two in there someplace. I'm unclear. So the journey is, it's about the software, stupid. I know that I can write things down byte addressable and they'll stay there. That's all I know. Right? I got to figure out how to do something with that.
So you're saying APIs, essentially APIs that are persistent aware.
No, and there's data structure design. There's APIs to access those data structures. There's other APIs to marshal those data structures to other people who want to use them.
Mm-hmm.
There's maybe some real-time transforms, like if I need an image as an EXR and the other guy needs the image as a TIFF, I don't want 2 files, I want 2 instances.
Mm-hmm.
Right? Stuff like that, times 500 million files.
All right, thank you. All right, so we have about 8-ish minutes. I have a question, and then we'll go back to the audience. You know, I'm seeing a lot of momentum here, a lot of good stuff around persistent memory. Besides cloning Andy Rudolph, what? I guess
life insurance.
what life insurance? I guess from my perspective, I would want to know from the panel. We have great momentum, but how could we screw up here? What do we need to watch out for? What are those pitfalls that would turn you off to this technology? Right.
Make it data center first as opposed to cloud first.
And what do you mean by that?
Data center only.
Well, that's even worse. So folks like me and those of us, my customers, need to be able to get a hold of this, feel the power, smell the power, and use it fast. And if we go through the typical adoption pattern where it takes, you know, a year for some Dell chassis, and then I'm still waiting for this, you know, the BOM for the Dell chassis that does whatever the heck it does, and then I have to wait for 6 months of procurement out of a financial services customer, and then 6 months to blah, blah, blah. It's going to take 3 years again, even after new things are out there. If I can just spin up a virtual machine and use it tomorrow that has this stuff on it, load my database on it, and then tell my financial services customer, well, I know it's in the cloud, so you can't use it really, but ... we can all move on this thing quickly. So to me, it has to be cloud first to enable adoption. Please do that. And if you don't do that, there's going to be this long stumble, and who knows what happens.
Totally agree. So cloud first. I mean, we went through, I mean, I can tell you the story about cloud. We talked to like Barclays about 3 or 4 years ago, massively conservative UK bank, right? 4 years ago, they said, Nikita, are you kidding? What cloud? You know, we're the bank. You know, there's millions of regulations. We don't even think about this, right? 6 months ago, they moved almost the entire banking pipeline into the cloud. Think about this. Most conservative UK bank. In 3 years, it's a huge bank, by the way, global bank. They went almost entirely to the cloud. So we need it in the cloud, first, foremost, to begin and the end. You know, our deployments, and then we have very large open source project. We have millions of downloads and hundreds of thousands installations. And our non-cloud installations is dwindling down catastrophically fast. Almost everything moves to the cloud. So if you don't have it in the cloud, it doesn't exist to the customers.
Thank you. All right, any other questions out there? Oh, we got one.
Hi. How are you guys going to handle the depression of finding out that persistent memory over fabrics, because doing this stuff at scale is what it's about, just turns out to be block devices with a block size of 1?
Why is that depressing? What's the problem?
It's not depressing.
It's a question about the apparent scale at which we're talking. What we appear to be doing is multiplying up the addressability and reducing the address size, and that appears to be what you guys appear to be interested in is stuff that's byte addressable, but that looks like storage, but it's not really handleable at the byte level as such. We still need to build file systems over this. We still need to
you need to build namespaces over it. You don't have to
Or
build a file
namespaces.
system.
Or databases.
Or databases.
Screw the file guys. Sorry.
Yeah, well,
Any file guys here?
no, it's funny. There's a few. But it's funny you say that. We have a group at DreamWorks, they call themselves NoFS. We're trying to get rid of file systems as the abstraction because users and our developers treat them like databases. And they're not. They're just hierarchical namespaces. And unfortunately, the name of the file and some extended attributes become the database entry, and it's impossible. But it's easy, and that's what they do. So to your point, there's the other difference between byte addressability is instead of reads and writes and serializing and deserializing, I'm just doing loads and stores. So the loads and stores part is interesting, and then all my data is just in the address space. That's the goal, is I can treat everything, billions of exaquad bytes as some offset in memory. The challenge there becomes the processor builders have to build me virtual address spaces with 128 bits or more so I can map everything. And that's a problem. Or physical pins coming out of the chip so I can talk to everything.
I think byte addressability, I mean, again, I'm going to sing the same song I've been singing. But byte addressability is the market for this technology, not block level device. That's my hardcore opinion. Because that will open millions of developers in the JVM stack, on the Python stack, anywhere. And until we get the proper byte addressability, that is baked in the operating system, available to everybody, that's still going to be niche stuff.
Yeah, I should also add, I think, I agree with the byte addressability. The other thing I would add is, all the metadata effectively can stay byte addressable. So you can have like persistent medium all over the place, and the metadata can just stay in persistent memory. And so everything that you need for your metadata is completely in persistent memory, and it's byte addressable. The one thing that I should add is we should do a lot more developer outreach than what we're doing right now. I think, like if you follow everything in LKML, if you got Andy Rudolph's cell phone number, then you got, you know what to do and how to do all this stuff. But we're really not, as a community, doing, a service in terms of, hey, here's how, you use it, and push that out more into the developer community. There's a handful of developers who know how to use it, but it's not yet pushed out. And what we got to do as a community is sort of get more developer adoption, get simpler APIs out to everybody for using this. And so that's something that I think we still need to do. And also, my pet peeve is, the RDMA implementation. I think there's like so many people who kind of know how to do it, but we don't have a standard way of doing it yet, across NIA, across the Link working group, across everybody else. And if we can just sort of say, look, here's the API, after a few years now, that would be really nice.
Yeah. The one problem with being a community of people who knew how to do things is we're commercial competitors, right? So, I mean, we've been in a couple panels before, right? I like GridGain a lot. But at the end of the day, there's going to be a few cases where we overlap, and so We have to meet in dark hallways. I have a friend at Oracle. I can't say to anyone who he is, but he's the guy who works on PMEM over there. And occasionally we work in a dark alley, meet in a dark alley and share some secrets. And we go home. And I can't tell anyone that, right? I can't tell people inside my company. I can't tell people at Oracle that. So there is a community, and there's the guys who have each other's cell phones and meet for beers once in a while. And that's sort of how Silicon Valley works. So I don't know how we can really do that much better, because we are competing in some sense.
There's a couple things. That's an argument for the cloud. It makes the stuff accessible to people outside of the secret society, right? Secret society people all have hardware and all know people that can get them hardware and have Andy's phone number. There are a lot
Which,
of
by the way, is area code. So.
But there's a whole bunch of people that probably want to try it but don't have one. Can't get a picture of one, but want to go maybe get some free cycles at Amazon to play with one, right? So I think that's an argument for the cloud first, for outreach, and for accessibility, and for try before you buy, for POCs, and for fail fast.
All right, we got time for one more question, and we're getting the hook
It's
soon.
going to be a fast question.
Okay, fast question.
It's Gene Bosman with Hurwitz and Associates. Just regarding our recent cloud discussion, could you just clarify a little bit? Were you talking about cloud technology, private cloud, or public cloud? Because I think a lot of this stuff is going to be done in the private cloud. That's just my own opinion.
Public.
You're public. And
Cloud means AWS. There's no other clouds.
you know what I'm saying? I
My man.
I don't know all the politics here, but there are private clouds. That's why I'm asking.
No, I wouldn't want it in the public cloud so I could try it. I wouldn't put potentially real data sets in there, but as of today, for me to get 100 developers to go play with something with persistent memory, I can't. It's just hard to do, mechanically hard to do. Got to get the right SKUs, got to get the right...
I might say there are 3 clouds if there's not one, but it really is what the case I was making for cloud and this technology is people like him need to have his developers click a button, get access to it, and try it. And the adoption cycle that I was describing of going out and buying a bunch of machines, then putting it in, then figuring out how VMware works on it, and then getting an upgrade to that, blah, 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 3 years. So it's got to be public cloud, and it's got to be the big ones that everyone uses.
Okay.
Single question like POCs. If you guys try to sell anything to the enterprise world, you want to try it out. Exactly the same story.
Well,
Try
anyway.
to even explain what the bank needs to do or any other organization needs to do to try out the NVM.
Yeah.
That's
All
a
right,
project in itself.
I did think it was
I think
important
we
to
are
clarify. Thank
out
you.
of time, but thank you, everyone. This concludes our panel. Thank you, wonderful panelists, and back to you, Jenny.